This is part 1 of my lecture on galaxies. Here I'll describe the discovery of galaxies, the 3 types of normal galaxies, and how we see galaxies moving inside and outside the local group. 100 years ago, people didn't know for sure that other galaxies exist. With the naked eye, you can see just 3 of them, but it's not at all obvious that they're galaxies. 2 of these are the Large and Small Magellanic Clouds, which are in the southern sky, and the 3rd one is the Andromeda Galaxy. The Magellanic Clouds look like clouds, and the Andromeda Galaxy just looks like a piece of cotton with the naked eye, even if you're at a place with no light pollution on a clear, moonless night. From the 1600s onwards, people started looking at the sky with telescopes and discovering new objects. In the 1800s, a comet hunter named Charles Messier made a catalog of over 100 objects that he had looked at that weren't comets and were therefore a nuisance to him. Here they are. At this point in the course, you should be able to identify what types of objects most of these are, even though each image is tiny. There are a bunch of star clusters, including open clusters like M45, the Pleiades. Many of these are globular clusters. There are star-forming regions like M42, the Orion Nebula. There are planetary nebulae, or sun-death nebulae, like M57, the Ring Nebula. And there are supernova remnants like M1, the Crab Nebula. And then there are many objects that appear flat or spiral. These were referred to as spiral nebulae. Here is a close-up of some nebulae. The one at the top is a sun-death or planetary nebula. The one at the bottom left is a star-forming region, and the one at the bottom right is a supernova remnant. These are all inside our galaxy, the Milky Way. How about the spiral nebulae then? Are they inside or outside the Milky Way? If they're outside, then each of them could be its own galaxy like the Milky Way. That would mean the universe is way larger and contains much more stuff than if the spiral nebulae are all part of the Milky Way. This was the subject of the so-called Great Debate between Shapley and Curtis in 1920. Shapley and Curtis were 2 of the leading astronomers. Shapley argued that the Milky Way was the entire universe and that the spiral nebulae are all part of it, while Curtis argued that each spiral nebula is an island universe. In other words, it's its own galaxy potentially containing as many stars as the Milky Way. Neither won. People left not knowing who was right. Now you might be tempted to think Shapley was an idiot to believe what he did, but no. This was the man who actually figured out where the center of the Milky Way is. He plotted the locations of all the known globular clusters and found that there are many more in one direction than in the other directions. In fact, they're concentrated around the constellation Sagittarius. Shapley correctly assumed that globular clusters must orbit the center of the Milky Way. So he figured out that we must lie on one side of the galaxy and that the center of the galaxy must be in the direction of Sagittarius. The problem was that there was no way to estimate how far away the spiral nebulae are. Shapley thought they must be relatively close and therefore inside our galaxy. As you've learned already, we can measure the distances to nearby stars using parallax. The further a star is, the smaller the parallax shift. The spiral nebulae didn't have any parallax shift, and so they had to be pretty far, but there were plenty of stars that didn't have any parallax shifts either. A few years before the Great Debate, a woman named Henrietta Leavitt made a discovery that would eventually allow us to measure distances to the spiral nebulae. Leavitt looked at stars in the Large Magellanic Cloud and found that many of them vary in brightness and that some of these, called Cepheids, get brighter and fainter at regular intervals. She didn't know how far away they were, but since they appeared to be part of a cloud, she assumed that they were all at roughly the same distance from the Earth. What she discovered is that the brighter a Cepheid is, the longer it takes to go from bright to faint to bright again. What this means is that you can use Cepheids as a distance indicator. If you discover a Cepheid and see that it has a period of 30 days, that means it's around 10,000 times as luminous as the sun. You compare this with how bright it appears to be, and that tells you its distance. The Large Magellanic Cloud is far. It's a couple 100,000 light years away. 15 years later, a man named Edwin Hubble would discover Cepheid variables in the Andromeda Nebula and show that it had to be its own galaxy. Hubble was born in Missouri and then moved to Wheaton, Illinois when he was 11. He loved astronomy, but his dad wanted him to become a lawyer. So he studied law at the University of Chicago and then went to Oxford, England on a Rhodes Scholarship and ended up getting his master's there as well. Then his dad died, and so Edwin moved back to Illinois, but he really didn't want to practice law. So he went back to the University of Chicago for a PhD in astronomy and got all of his data from the 24-inch telescope at Yerkes Observatory, which was still one of the largest in the world. Then he went off to fight in World War I and then did astronomy for a year at Cambridge before moving back to the US. He got a job in California where a 100-inch telescope had just been built. Edwin Hubble was one of the first to use it. He pointed it at the Andromeda Nebula and saw stars inside it for the first time. So you can see that it's not just a nearby cloud of gas that doesn't contain stars. It's a distant object that contains stars that are too faint to see with smaller telescopes. Some of the stars he sees in Andromeda are Cepheids with very long periods. This means they're very luminous. They only look faint because they're so far away. Hubble uses Leavitt's period luminosity relationship to measure the distance to the Andromeda Nebula. It's a couple million light years away. Hubble writes Shapley a letter where he says, "You will be interested to hear that I found a Cepheid variable in the Andromeda Nebula." If we translate what he goes on to say to present-day speech, it's basically, "Sorry, dude, you're wrong. Curtis is right. You've lost the debate." Up until then, Shapley had been very attached to the idea that the Milky Way is the entire universe and had fiercely defended this. But this is science. It's all about the data. And the data clearly showed that he was wrong. So Shapley told a friend, "Here is a letter that has destroyed my universe." So Hubble became the father of extragalactic astronomy. He was the first person to show that there are things beyond our galaxy. He would go on to make other great discoveries, one of which I'll get to soon. He never got the Nobel Prize, though, because it wasn't awarded to astronomers. Hubble was quite upset about this. He argued that astronomy should be treated as a branch of physics. It was only after his death that the Nobel Prize in Physics has been awarded for discoveries in astronomy. Let's look at the three types of normal galaxies, starting with spirals. When viewed at low inclinations, meaning nearly face-on, we can see the spiral arms. Here's an optical image of a spiral galaxy on the left and an X-ray image of the same galaxy on the right. The colors are arbitrary on the X-ray image, but on the optical image we can see that there are a lot of blue regions in the spiral arms, but not in the central portion, which is called the bulge. We also see more dust and glowing nebulae in the spiral arms than in the bulge. Here is another low inclination spiral on the left and a high inclination or edge-on spiral on the right. On this one, we can clearly see that the bulge is distinct from the flat disk. It's like a round ball that lives at the center of the disk. We see the near side of the disk passing in front of the bulge, but the bulge does not appear to contain any dust, blue stars, or glowing gas clouds. On the nearly face-on spirals I've shown you so far, the arms spiral in all the way to the center. But on the one shown here, they stop abruptly, and then there's a bar that goes through the center and then connects to an arm on the opposite side. This is called the barred spiral. The others are called unbarred spirals. Why is it that some spirals have bars while others don't? Really, no one knows. This is one of the areas I used to work on. One idea is that bars can form from instabilities in the disk. It's even possible that bars can funnel material from the disk to the bulge. Normally, bulges shouldn't contain dust, but here we see dust lanes in the bar going from the disk to the bulge. Let's now move on to elliptical galaxies. They have much less going on than spirals. No spiral arms, no disk, no dust, no glowing gas clouds, no blue regions. It's the same color throughout. Ellipticals contain yellow, orange, and red stars, but not blue stars. Then we have irregular galaxies, such as the Large Magellanic Cloud, shown here. As the name suggests, they're neither spiral nor elliptical. But they seem to contain a lot of things that spirals contain, which ellipticals don't. There's dust. There are glowing nebulae. This is the Tarantula Nebula, one of the largest and most active star-forming regions known. The fact that the galaxy looks blue also tells us that it's forming new stars. That's because blue stars don't live long. Remember, the blue main sequence stars, which are more massive, hotter, larger, and more luminous than the yellow and red main sequence stars, have much shorter lifespans. If a galaxy or a part of a galaxy doesn't look blue, what does that mean? It means that it doesn't contain blue stars. Blue stars can't hide. If they're there, you'll see them. This means elliptical galaxies and bulges of spiral galaxies don't contain blue stars. All other blue stars have died and no new ones have formed. This means ellipticals and bulges no longer form new stars. The disks of spiral galaxies and irregular galaxies do form new stars. They contain old stars as well as young stars. The blue stars outshine the red stars. This galaxy actually contains far more red stars than blue stars, but we don't notice them because they're so faint. Here is the Andromeda Galaxy, Messier 31, along with two of its companions. M31 is a large spiral, even larger than the Milky Way, while the other two galaxies we see here are dwarf ellipticals. There's M32 here and M110 over here. Ellipticals aren't necessarily small. These happen to be dwarf ellipticals, but there are giant ellipticals as well. Here are some of the galaxies in the local group. The two large ones are Andromeda and the Milky Way. Everything else is a satellite of one of these two. While groups contain a few dozen galaxies, a cluster can contain hundreds or thousands. Here we see one that appears to have two dominant galaxies, surrounded by plenty of small ones. During the 1920s and 1930s, Hubble and other astronomers obtained spectra of hundreds of galaxies. They found that all the ones outside of the local group are redshifted. That means they're all moving away. The further they are, the faster they're moving away from us. This is now called the Hubble law. The velocity with which a galaxy is moving away from us is related to its distance by a constant called the Hubble constant, h0. This can only mean one thing: the universe is expanding. We can use the Hubble law to estimate the age of the universe. Here's the basic idea. Speed is distance divided by time, and so time is distance divided by speed. So if you want to know how long a galaxy has been moving away from us, that must be related to the distance to that galaxy divided by the speed with which it's moving away. Now the Hubble constant is speed divided by distance. So 1 divided by the Hubble constant must be related to the age of the universe. There are plenty of complicating factors, so the actual formula is more complicated, but we can use the Hubble constant to get the age of the universe, and we find that it's close to 14 billion years. So in every direction in the sky, every galaxy that's beyond the local group is moving away from us, and the further they are, the faster they're moving away. So it appears as if we're at the center of the universe. What are the odds that we happen to be located right at the center of this huge universe containing billions of galaxies? Also, all motion is relative. If we see a galaxy moving away from us, if there were aliens living there who can see the Milky Way, they would see it moving away from them. Are we moving with them sitting still, or are they moving with us sitting still, or are we both moving? There's actually no way to tell. All we can say is that the distance between us is increasing. These aliens wouldn't just see us moving away. They would see all the other galaxies outside their group or cluster moving away from them as well. So wherever you are in the universe, you should see distant galaxies moving away from you. So none of them is at the center of the universe. There is no center in the observable universe. Every place is moving away from every other place. This, I think, is the most mind-blowing concept in all of astronomy. Here's an analogy. You'll probably find it helpful, but don't expect it or any other analogy to fully satisfy you. Picture ants on a balloon that's being inflated. These ants have no idea that there's a world beyond the surface of the balloon they live on. They also can't see the curvature of the balloon. Each ant sees other ants in every direction. They're all moving directly away. So each ant thinks it's at the center of an expanding universe. Now you might think, silly ants, none of you's at the center of the balloon. There is no center on the surface of a balloon. The center is inside the balloon, which you can't get to. But the ants don't know about the inside of the balloon, or for that matter, the outside. The surface of the balloon is their entire observable universe. We find ourselves in a similar predicament. In this metaphor, everything in the three-dimensional universe we can see is actually expanding into a higher dimension we can't see. No place within the observable universe is any closer to the center of the universe than any other place. We can't visualize a universe with no center for the same reason we can't visualize a universe beyond 3 dimensions. Our eyes and brains have not evolved to perceive more than 3 dimensions. We haven't needed to in order to function in this world. Here's another analogy. Imagine you bake some bread with some raisins in it. You start off with dough, and as it turns into bread, it expands. Let's say 2 raisins were initially 3 centimeters apart. Now, they're 6 centimeters apart. How about 2 raisins that were initially 7 centimeters apart? They're not 10 centimeters apart now, they're 14 centimeters apart. The further apart they were to begin with, the faster they're moving away. This is like our universe. The raisins are like galaxies. Actually, they're more like groups or clusters of galaxies. The raisins aren't expanding. Likewise, the solar system, the Milky Way, and even the local group aren't expanding. We're not moving away from Andromeda or the Large Magellanic Cloud. But every group is moving away from every other group and every other cluster. The bread is like the space between galaxies. Rather than thinking of a galaxy as moving away from us, it's better to think of the space between us as getting stretched.